you so much for coming to my thesis talk this afternoon. My name is Alan, and today we will be talking about searching for oscillations and searching for small-scale magnetic structures from the 2017 Williams College Total Solar Eclipse Expedition to Oregon. So let's see, going to the next slide. All right. So there's a lot of ground to cover, so I'll go through the highlights of each part. So first we'll start with the background information and the introduction. So this is our current understanding of the sun's structure. So we can see there are layers of the sun. We will focus on the sun's corona, which is the atmosphere of the sun. Specifically, we're interested in wave oscillations in the corona and comparing that to the photosphere. So our question at hand is, why is the corona, the outermost atmosphere, significantly hotter than the photosphere, or surface of the sun? And how is the corona heated? Even though it's farther away from the center, why is it so much hotter than the surface of the sun? So one important assumption for us is that oscillations on magnetic constrained loops of coronal gas are one of the main mechanisms for the corona's temperature to be heated to millions of degrees. So for my thesis, we will talk about the search for the existence of oscillations, and we'll determine the period ranges by looking for significant peaks on the power spectrum as ramifications for the theories of coronal heating. So we'll go over some important background information about our data collection and what makes the total solar eclipse so special. Now, because the surface of the sun is so bright and the Earth's sky is so blue, we cannot normally view the corona since it is fainter than the blue sky. We get a great opportunity to view the corona in its purest form during the totality of a solar eclipse. That is when the sun itself is actually blocked, completely blocked by the moon. And this is really rare to be seen. Total solar eclipse occurs on average somewhere on Earth, once every 18 months. And keep in mind, it also has to be clear skies and during the daytime. So for our investigation, we're focusing on the data set collected in the 2017 total solar eclipse at Salem, Oregon. And this one is especially special since it crossed the entire continental US. It lasted for about 2 minutes, and we see the vast expanse of the partial eclipse. It's viewable through the entirety of North America. But we're focusing in on the continental US, and we see about 2 minutes of totality at Salem, Oregon. And we actually collected 92 seconds of usable data, which is quite impressive. So here we can see the coronas. The corona is in a composite image here, and it's during that same total solar eclipse. This is another beautiful composite by Professor Pasikov and Wendy Carlos that really showcases the solar corona, extending far into space. And this is a progression of the same solar eclipse. Thank you to Kristen Lockwood, who presented earlier, for these composites. Again, our data source stems from the totality phase, which is the top right one, and that is where our data is coming from. So on to some research and mathematical theories. So it's really interesting. This investigation has been going on for a while. 5-minute or 300-second oscillations have been speculated and confirmed before. So through the last couple of decades, Williams students have been busy at work investigating related topics. So what's great now is that we're looking for oscillations in the scale of seconds instead of minutes. Now that we have better technology and higher computing power, we're searching for the existence of oscillations by looking for significant peaks on the power spectrum as ramifications for the theories of coronal heating. And moving on to some mathematical theories. So in summary, the data collected, we were focusing on the intensity of the flux value, the coordinate system, which is the x and y values, and the frame number, which actually corresponds to time for images. And each frame represents an image taken, and there is a constant 0.3517 seconds between each frame taken. So our data processing methods involve an array of mathematical and analytical tools in order to search for oscillation peaks. So a really remarkable and quite powerful mathematical idea here is the Fourier transform. That helps to detect and characterize periodicity of flux signal over time. Now, this is a mathematical tool that can separate complicated periodic sinusoidal functions into its smaller constituent parts. And it can decompose all of these complicated functions into just basic sine and cosine functions. It can help to identify the possible oscillation patterns upstream of the electromagnetic waves from data observed during total solar eclipses. Now, this idea has influenced what's called the Loam-Scargill periodogram. It's motivated by the aforementioned Fourier transform analysis, and this is pretty powerful, especially in astrophysics. It's a well-known algorithm for detecting and characterizing periodic signals. Now, this is even more powerful than just the Fourier transform, because it works for both evenly and unevenly sampled data. So there's actually quite an interesting backstory to how this got developed, but in summary, it was developed independently of the Fourier transform, and it involves discrete data sets being approximated by weighted sums of progressively determined frequencies, and we're actually using concepts of standard linear regression or least squares in order to fast fit. So this was later simplified and connected to periodogram analysis as in the Fourier transform. What's great about the LSP is that it's available in many programming packages, such as AstroPy, which we can implement in Python. So we will use the LSP to search for the existence of oscillations by looking for significant peaks on the power spectrum as ramifications of the theories of coronal heating. So again, the LSP is inspired by the Fourier transform, and we see two cases here, continuous and discrete. In our case, we're working with data values, discrete data values, so we're focusing more on the discrete case. And this is the equation that we actually use to implement it. So a periodogram is a power versus period graph, and another word for that is called the power spectrum. So two remarkable scientists, Loam and Scargill, they developed this method of transforming flux versus time to power versus period or frequency, essentially transforming from the time domain to the frequency domain. And please note that frequency is just, and period, it's just they're inverses of each other. One over the other yields the other. So if we look at the equation here, we see xj is the flux value. We input that. That is basically it corresponds to the brightness or the flux. And then time is basically for each frame, that's a time. The output value, we have Loam-Scargill power. And then we have omega representing frequency and tau representing time delay. And it's defined by the following. It's interesting to note that the main equation up here was developed first, and then the second part was developed later. So on to how we use these concepts in data and methods. So yeah, this is a portion of the sun, and we're focusing on the selected square portion for our data analysis. And a huge thank you to Dr. Michael Person from MIT as part of the Williams College expedition. Dr. Person got the data using the telescopes and filters listed here. He also played a big role in advising his thesis. And we see the filters used here are the green filter and the red filter, and they correspond to iron 14 and iron 10. So the combination of these two filters can provide us with more comprehensive information about the solar corona. We refer to them as the green series and the red series. So over here we can see the visual representation of the green and red series. So basically this illustrates that the coronal loops taken at the red and green emission lines are observed at different locations. So basically, we have our data. They're stored into FITS files. We actually have 270 consecutive frames with the constant time interval, as I mentioned, between them. And we have 92 seconds, the total time that we have. And then the green series was started before the red series. So we're taking that into account when we process our data. So if you'll please turn your attention to the application. So this is what we use for processing the data. So I'll just briefly stop sharing and then reshare my screen in order to see the application over here. So if you can see my screen now, this is the green filter and this is the red filter. So basically for the green filter, we can see as we move along, as we scroll along in time, we see the sun actually sliding down. The same with the red filter, we see sliding down of the sun. And we have to account for that when we're working for our data. We need to make that constant. And then back to sharing my PowerPoint here. So that's one thing we have to take care of. Also, in the green series and red series, we see that they're misaligned between each other too. So the area between the gray lines are actually where we will analyze the data. That's a physical location, same physical location on the sun. So as we mentioned, there's the within problem and the between problems, and we have to make corrections for this. So the key is to find the center of the circle for each frame, and we have to match the green and red series in all the frames. So we use the equation of the circle, and we use the assumption that the sun and moon are approximately circles as 2D representations. So because of time constraints, I won't go into our statistical analysis in detail, but we do perform some statistical analysis, and we fix the radius value for the pixels. And then we use a Python, and we use a AstroPy class in LumTurtle in the library to transform the data for flux versus time. So basically, we have 1,534 of these squares, 3 times 3 squares, and then we have that for each of the color series, both the green and the red color series. So moving on to results and discussion. So here we see that there are 4 representative points in sample results. So A and B are actually representative sample squares. So for A, those are the black marked spots, and non-black marked spots are green. So we see here an example of the power spectrum. The top graph is the flux versus time plot, and that's raw data. The bottom graph, after we perform the LumTurtle transformation, we get the periodogram. So here we do see a significant peak after we perform the LSP transformation, and that's around a period of 8 seconds. The same with the green. So this is actually A prime, so it's actually this over here on a green frame. And we see 3 significant peaks here, 2 at 4 seconds and 1 at 6.5 seconds. And then we can do some more detailed analysis, and then we can find, grouping these together, there are indeed specific significant peaks at the black marked squares. This contrasts sharply with the non-black squares, and there are no significant peaks found. So we do this for all the data we have, and it looks like the black box oscillations are only found extremely close to the solar limb. And some conclusions that we have are basically, number 1, observed oscillation peaks, we found them for flux with specific periods. So for the red series, 8-second periods. For the green series, we have 2 periods around 4 seconds and 1 period at around 6.5 seconds. Another conclusion that we can make is that these oscillations are observed only very close to the sun's surface, and our results indicate that significant peaks in the periodogram seem to be related to the sampling source distance from the sun and not to the brightness of the sampling source. So there's a lot of insight. If I had more time, we can talk about this. So yeah, so some possibilities for extensions in the future are that we can compare this data with data from other sources, and even the December 2020 eclipse coming up that Williams College is planning to go to. And we focus on the corona regions between the 2 gray mark lines. We can focus on other colored series as well as outside of that region. And yeah, thank you so much. Thank you especially to Professor Jay Pasikoff of the Williams College Astronomy Department, to Michael J. Person of MIT, and Professor Mahai Soichu of the Williams College Mathematics and Statistics Department.
All right, thank you, Alan. So again, questions can be sent either through the chat or raising your hand through the Zoom function. And got time for questions. All right, first question from Professor Jensen. You should be unmuted.
Yep. Thanks for the talk. I was wondering why, I guess you gave a little bit of background on the LSP method and how it mathematically compares to the Fourier transform method a little bit. But I was wondering, and maybe I just missed this, but what advantages does LSP have for what you're doing over maybe more traditional Fourier transform or other frequency analysis methods? Or is it kind of a, I guess what motivated that choice and what advantages might it have?
Yeah, thank you for asking that. That's a great question. So the LSP is actually more powerful than the Fourier transform because it can deal with both evenly and unevenly sampled data. And it's very helpful for implementation on Python when we are working with a huge data set. And it's readily available in Python. And basically, we have more specifications on what parameters to change. So yeah, it's become more of a standard in astrophysics now versus the Fourier transform.
I think you commented on your previous slide that your data was evenly sampled. Is that correct?
Oh, yes.
Yeah. So you didn't have that. You didn't need that, I guess, feature necessarily.
Yeah, we didn't need to actually feature it, but it looks like because of the discrete nature of LSP, that's an industry standard, and the computing power for that, it's actually even more convenient for implementation in Python. So that's the reason.
Great.
So thank you for Dr. Person from MIT for introducing me to this package.
Thank you.
Next question from Professor Stoichiu.
Hi, Alan. Thank you for your talk. I wanted to ask you if you could tell us a little bit about the large peaks when you take the LSP transform. So how did you choose, and what did you choose to call a large peak?
Oh, yes. Thank you very much. So a significant peak here is actually defined as a peak that is 2 or more times higher than the surrounding peaks. So these significant peaks are very important because those are the most important oscillation pattern, the constituent simple sinusoidal functions at around a period of 8 seconds in this case, and around a period of 4 seconds and 6.5 seconds in this case for the green filter. So these really highlight what is prevalent in the raw data we have, and it can separate the chaos into very identifiable and beautiful patterns that can help us have more evidence and ramifications for the theory of kernel peak.
Other questions for Alan? So I'll ask one question. So you mentioned sort of how to track different positions or how the pixels moved. I'm sorry, how the sun, in fact, is moving across the pixels and how you use that to map. So were you trying to identify essentially common locations relative to, say, the center of the sun for the 2 different filters? Is that what you used when you finally did the final reduction here? Is that right?
Yeah, so that actually was the most interesting part, or the part that took the most creativity in order to solve here. So basically, the key is to find the center of each frame, and then we have to match all the green and red series for all the frames. So there's 2 problems that we have to solve simultaneously. So we do have a circle here, and then the center of the frame. The center is actually, we mark our areas based on both delta x and delta y, as you can see here, and also the radius of the sun-moon complex, which I showed you on the external program. And I think this would be very helpful to illustrate too. So I will share this marked screen over here, and we can see that this is an example of the same picture that we have, but this time the difference is we have a sample marked box here. So that box, as we move across, as you slide, it's actually on this, that represents the same location of the sun. And yeah, can you see that right now on the screen? Yes. So that is actually constant, and we have to make that constant. And then that was a huge part of what we had to do. And then that's one of the problems. And we also had to solve the problem for the between to match the red series and the green series.
So Professor Pasakoff, you are now unmuted. Sorry about that.
Okay, hi. It's been a pleasure to work with Alan, who took my heliophysics seminar in the fall, and we've brought in Mike Person from MIT and Mihai Stoichev from Math Stats Department. I think some of them are listening, so it's fun to broaden this. And Christian earlier has also been collaborating with some of our people from other institutions, so I'm glad we have these good eclipse data, and there's still work we can do on them, and we're hopeful that the travel is unmuted enough that we can go to the December 14th, 2020 eclipse in Argentina and continue both these projects.
Thank you so much, Professor Pasakoff. It's been such a fun experience, so much learning about so many disciplines.
All right, wonderful.
I guess behind my head, but the background is during the eclipse in Chile last July.
All right, I'm going to unmute everybody so we can give a claim to all of the wonderful thesis presentations today. Here.
Everybody.
Well done. Okay, and so for those of you who want to now participate, I suggest you turn on your cameras. I don't exactly know how this is going to work, but you know, I just want to thank everybody for persevering during these interesting weeks since I guess March 13th, Friday the 13th. But you all made it, and was very happy to see all of these wonderful talks. And I'd like to